There is a timber frame barn standing in England right now that has been holding its roof up since 1292, over 700 years. No steel plates, no synthetic adhesives, no structural engineer. Now walk into the average modern timber home after 15 years. Cracked beams, rotting sill plates, joints pulling apart. The medieval barn is still standing. Your modern frame is already failing. This is not luck. This is not some mystical lost craft. This is biology, chemistry, and a set of principles so devastatingly effective that we need to ask one very uncomfortable question. Why did we abandon them? Before I tell you why medieval timber frames were basically indestructible, I need to tell you something that most people get completely wrong when they look at old buildings. The frames still standing today? They are not average. They are the survivors. Every badly built frame, every poor timber choice, every sloppy joint. Those are gone. They rotted, collapsed, or got demolished hundreds of years ago. What you're looking at when you see a 700-year-old barn is the best of the best, the ones that got everything right. And when you study what those survivors have in common, a pattern emerges. Consistent, deliberate, technically sophisticated. This was not happy accident. This was a system. A complete approach to building with wood that treated timber as a living biological material with its own chemistry, its own movement and its own rules. Here is a number that should bother you. The Merchant Adventurers' Hall in York, built between 1357 and 1361. Core oak frame still structurally sound, still in use, over 650 years. Now here is another number, 4, as in years. A timber frame house in Vermont, documented in a published case study, was approaching catastrophic structural failure at 4 years old. The sheathing was rotting, the frame was compromised, the building was not even a decade old. Same material, completely different outcome. And the gap between those two buildings is not the century they were built in. It is the system that surrounded the timber. That system starts long before the first joint is ever cut, and that is exactly where we are going next. Modern timber production operates on one principle: speed of return. A plantation softwood tree reaches harvestable diameter in 25 to 40 years. It is felled, milled, dried, and on a building site within months of leaving the ground. The oak that framed the Merchant Adventurers' Hall was probably 150 to 200 years old when it was felled. That age difference is not just a number. It is the entire foundation of why medieval timber performed differently from modern lumber. And the mechanism is cellular density. A slow-growing oak in a managed wood pasture or ancient wildwood produces narrow annual growth rings. Each ring represents 1 year of growth. In a fast-growing plantation tree, those rings are wide, meaning the tree added a large volume of wood each year. In a slow-growing medieval oak, those rings are so tight that you can count over 100 of them in a single inch of cross-section. The structural portion of each growth ring is called latewood, the dense dark band that forms in late summer when the tree slows its growth and produces thick-walled cells. In a slow-grown tree, the ratio of latewood to earlywood is dramatically higher than in a fast-grown tree. More latewood means higher density. Higher density means higher mechanical strength, lower moisture absorption, and greater resistance to the fungal decay that destroys modern lumber within years of exposure. 1 cubic foot of old-growth medieval oak weighed significantly more than modern plantation softwood. That weight is not a liability. It is the physical expression of cellular density. It is the reason a medieval post could lose 30% of its surface to weathering over 200 years and still carry its load, because the remaining core was so dense, so strong, that the degradation was essentially cosmetic. Modern structural softwood sized to the minimum required by building code has no such margin. The moment decay begins, structural capacity begins failing. There is no reserve. The tree was harvested before it had time to build one. Here is the part of this story that nobody talks about, because it requires understanding a little chemistry, but it is the most important mechanism in the entire system. As an oak tree matures, the inner sapwood cells die and undergo a chemical transformation. They become impregnated with polyphenolic compounds called extractives. In oak, these are primarily hydrolysable tannins, elegitannins, gallatannins, The same compounds that make oak wine barrels preserve their contents for decades. The same compounds that make oak bark the traditional material for tanning leather. This transformed inner wood is called heartwood, and it is chemically, biologically and structurally a completely different material from the outer sapwood. Sapwood is alive. It transports water and nutrients. It is rich in starch and sugar. It is, from the perspective of a wood decay fungus or a wood-boring insect, a perfect food source. Sapwood exposed to moisture will begin to decay within years, sometimes within months. Heartwood is chemically defended. When a decay-producing fungus attempts to colonize oak heartwood, it secretes enzymes to break down the wood's structural polymers, the tannins in the heartwood complex with those fungal proteins, and precipitate them. They neutralize the organism's ability to digest the wood before it can establish itself. White oak heartwood goes further. It contains tyloses, froth-like growths that physically plug the wood's pores, making it virtually impermeable to liquid water. This is why white oak is used for wine barrels. The liquid cannot penetrate, the fungus cannot establish. The wood endures. Medieval carpenters understood this distinction completely. They graded out the sapwood. Structural members were heartwood only. The pale outer ring of sapwood was either discarded or used in non-critical secondary components, where decay was not a structural concern. Modern timber production does not make this distinction. Grading rules permit the inclusion of sapwood in structural members as long as it does not affect the initial bending strength. The sapwood is there, it is in your walls, and the moment moisture reaches it, which it will, it begins to decay. The modern industry attempts to compensate with pressure treatment, copper-based biocides forced into the wood under pressure. But these treatments are superficial. They penetrate the outer layers. If the wood develops checks or cracks, and it will, moisture bypasses the treated zone and reaches the vulnerable, nutrient-rich interior. The treatment fails at exactly the moment it is most needed. The medieval oak did not need treatment. Its defense was built into its biology over 150 years of growth. You cannot pressure treat that into a 30-year-old plantation pine. Here is something that will seem counterintuitive. Medieval carpenters often built with green, unseasoned timber, freshly felled oak with a moisture content exceeding 50%. Modern building wisdom says this is wrong. Timber must be dried before use, kiln dried to a controlled moisture content. Otherwise it will shrink, crack and distort after installation. But the medieval carpenter was not making a mistake. He was exploiting a property of green oak that modern kiln drying destroys. Green wood is dramatically easier to work than seasoned wood. The hand cutting of complex mortise and tenon joints, the precise scribing of scarf joints, the shaping of curved braces, all of this is far more achievable in green timber than in wood that has already hardened through drying. The medieval carpenter cut his joints with precision in green wood, erected the frame, and then let the building itself do the seasoning. Protected by the roof from rain, exposed to natural airflow, the frame dried slowly over several years. Not weeks, years. And that slow, gradual drying is fundamentally different from what happens in a modern kiln. Kiln drying uses high temperatures, sometimes exceeding 170 degrees Fahrenheit, to rapidly remove bound water from the cell walls. The exterior of the timber dries and shrinks faster than the interior. The outer shell hardens and contracts around a still wet core. This is called case hardening. The internal stresses eventually relieve themselves through honeycombing, internal cracks invisible from the surface, or through deep surface checking that compromises both the structural integrity and the weather resistance of the member. In a medieval frame, the seasoning happened in situ. The wood moved. The joints accommodated that movement, and the oak pegs that locked the joints were typically drier than the green timbers they secured. As the green beams seasoned and shrank, they contracted around the dry pegs. The joint did not loosen, it tightened. The shrinkage of the timber drove the connection together with forces that no metal fastener can replicate. A medieval mortise and tenon joint, properly drawbored with a dry oak peg, gets stronger as the building ages. A modern bolted connection gets looser as the wood moves seasonally around the rigid metal. The structural logic of a medieval timber frame is built entirely around wood-to-wood contact. The mortise and tenon joint, the scarf joint, the lap dovetail, the tusk tenon, each one designed to transfer load across the full bearing surface of the connection, distribute stress across a large area of wood fibre, and accommodate the natural hygroscopic movement of the timber without catastrophic failure. The drawbore technique is the masterpiece of this system. The carpenter cuts a mortise in the post and a tenon on the beam. He drills a hole through the mortise walls. Then he drills a slightly offset hole through the tenon. When a tapered dry oak peg is driven through the assembly, it acts as a wedge. The offset forces the tenon to draw deep into its housing with enormous mechanical force. The joint is pulled together, not just held together. No adhesive, no metal, just geometry and the mechanical advantage of a tapered peg through an offset hole. Modern construction uses steel plates, bolts, and self-tapping screws. These connections have high initial load ratings. They are fast to install. They are consistent and predictable in laboratory conditions. But they introduce failure modes that the medieval carpenter never had to deal with. Wood is hygroscopic. It expands when it absorbs moisture and contracts when it dries. This movement is not small. Tangential shrinkage in oak from green to air dry can reach 7 to 8%. A large timber beam can move significantly across its width with seasonal humidity changes. Metal is rigid. It does not move with the wood. The wood wants to shrink. The bolt holds it. The wood splits around the bolt to relieve the stress. The very fastener meant to hold the connection together becomes the mechanism of its failure. Steel also has high thermal conductivity. In a heated building during cold weather, a steel bolt can conduct temperature from the cold exterior to the interior of the connection, reaching the dew point and causing condensation inside the joint. That localized moisture promotes decay at the exact center of the structural connection. Bolt rot. Hidden inside the joint where no inspection can reach it until the connection has already failed. And then there is the chemistry. The tannins that protect oak heartwood react with iron to produce blue-black staining and active corrosion. The same chemical defense that protects the wood from fungal attack attacks the metal fasteners holding it together. Medieval oak pegs do not corrode. They do not conduct cold. They do not create stress concentrations. They move with the wood because they are the same material as the wood. The diversity of historical joinery reflects the sophistication of the system. Scarf joints joined shorter timbers end to end to create long spans, using complex geometry to resist both tension and compression simultaneously. Tusk tenons provided wedged connections that could be physically tightened over time as the wood shrank. Knee braces converted lateral wind loads into compression forces that the frame could carry efficiently. Each joint type was designed for a specific stress profile. The medieval carpenter did not have one connection solution. He had a library of them, each matched to its structural context. Here is the failure mode that destroys more modern timber frames than any other single factor. And it has nothing to do with the timber itself. It is the wall system surrounding it. Modern building science is obsessed with airtightness and vapor control. Vapor barriers, airtight membranes, rigid foam insulation. These systems are designed to maximize energy efficiency by preventing air and moisture movement through the wall assembly, and they do that effectively. But they create a catastrophic secondary problem. When moisture enters the wall cavity, which it always does eventually through imperfect detailing, air leakage, or condensation, it cannot escape. The same barriers that prevent moisture entry also prevent moisture exit. The wood stays wet. The moisture content climbs above 20%. Fungal decay begins. And because the rot is hidden behind impermeable layers, it is invisible until the structural damage is already severe. 2 case studies published in the Journal of Light Construction document this failure mode with brutal clarity. A 4-year-old timber frame house in Vermont, with foam sheathing and a compromised vapor barrier, was approaching serious structural damage. The rot followed the post and beam framing pattern exactly, concentrated at the interfaces between the rigid foam and the structural members. The assembly had trapped moisture against the wood and provided no drying pathway. A second case documented severe rot in pine board sheathing following the post and beam framing of an 8x8 hemlock structure. The layer stack, interior poly, fiberglass infill, exterior diagonal boards, rigid foam and clapboards had created a system where wetting could occur through air leakage and flashing defects, but drying was blocked in both directions. The frame material was sound. The surrounding system destroyed it. Medieval frames were infilled with wattle and daub, lime plaster, materials that are highly permeable to water vapour. When moisture reached the timber, it could evaporate through the porous infill. The wood dried. The moisture content dropped below the 20% threshold required for fungal activity. Heritage conservation guidance is explicit on this point. The introduction of impermeable materials into traditional timber frames, cement renders, modern paints, misplaced vapour barriers, dramatically increases decay risk by trapping moisture against the structural members. The breathable envelope is not a quaint traditional preference. It is the moisture management system that keeps the timber alive. Modern structural engineering operates on the principle of efficiency. Calculate the exact loads. Size the members to the minimum required factor of safety. Use the least material that meets the code. This approach minimizes cost and maximizes speed of construction. Medieval builders had no ability to calculate exact stress loads. They could not run finite element analysis. They could not determine the precise bending moment in a principal rafter. So they did something that modern engineering has largely abandoned. They overbuilt, deliberately, systematically, and with extraordinary results. A 12-inch oak post in a medieval barn was often carrying a fraction of the load it was capable of bearing. The excess capacity was not waste, it was insurance. If that post lost 30% of its cross-section to surface weathering over 200 years, the remaining core was still more than adequate for the structural demand. The building continued to stand while the degradation was gradual, visible and repairable. A modern post size to the minimum code requirement has no such margin. The moment decay begins reducing its cross-section, structural capacity begins failing. There is no reserve. The efficiency that made it economical to build becomes the vulnerability that makes it dangerous to maintain. The redundancy extended beyond individual member sizing to the entire structural system. Medieval frames used numerous diagonal knee braces and wind braces to create multiple load paths through the structure. If a single member was compromised, the load redistributed through the remaining bracing network. The building sagged, it deflected, it gave visible warning, but it did not collapse. Research on traditional timber frames subjected to lateral loading confirms this behaviour. The knee braces carry significant compression and tension forces under racking loads. Doubling the stiffness of the brace-to-post connection substantially increases the global lateral stiffness of the entire frame. The bracing is not decorative, it is the lateral resistance system. And because it is distributed throughout the frame rather than concentrated in a few shear panels, the failure of any single element does not trigger progressive collapse. The flexibility of the pegged joints amplified this resilience further. Under seismic or wind loading, the joints could rotate slightly, dissipating energy through friction and bearing rather than transmitting it as brittle fracture forces. The building moved, it absorbed the load, it returned to position. Modern rigid connections transfer those forces directly to the weakest point in the assembly, which is usually a bolt hole or a notch, and that point fails suddenly. The decline of timber framing began in the 19th century with the balloon frame and mass-produced dimension lumber. The Industrial Revolution needed housing fast. Skilled carpenters who could cut a drawboard mortise and tenon joint were expensive and slow. Unskilled labourers who could nail dimension lumber together were cheap and fast. The guild system that had enforced quality through the threat of expulsion was replaced by standardized grading rules that prioritized initial strength over long-term durability. The nuanced understanding of heartwood versus sapwood, of slow-grown density versus fast-grown porosity, of green framing versus kiln drying, was replaced by a number on a grade stamp. And the concrete foundation, introduced as a modern improvement over the stone plinths and timber sill pads of traditional construction, created a new failure mode that the medieval builder never encountered. Concrete traps moisture at the base of the wood. The sill plate, the lowest horizontal member of the frame, sits in direct contact with a material that wicks ground moisture continuously. Sill rot is now the primary reason for the structural failure of modern timber homes. The medieval sill sat on a stone pad or plinth wall that allowed airflow and drainage beneath it. The wood stayed dry, the wood lasted. But here is what is changing. 6-axis CNC timber cutting machines can now produce drawboard mortise and tenon joints with the same precision as a master medieval carpenter, in a fraction of the time. Mass timber construction using cross-laminated timber and glulam is recovering the thermal mass and structural redundancy of solid wood construction. Heritage conservation organisations are publishing detailed guidance on breathable wall systems, lime plaster, and vapour open assemblies that protect timber frames the way traditional materials always did. The knowledge was never lost. It was set aside because cheap energy and cheap materials made it temporarily unnecessary. Now that timber frames are failing at 15 years, and energy costs are rising, and building regulations are beginning to mandate durability alongside efficiency, the medieval system is being rediscovered one research paper at a time. The medieval carpenter did not build frames that lasted 700 years because he was lucky. He built them from trees that had spent 150 years building their own chemical defence. He selected heartwood and discarded sapwood. He cut joints that tightened as the building aged. He surrounded the frame with materials that let it breathe. He overbuilt every member so that time could take its toll without taking the building. And then we replaced all of that with plantation pine, metal connectors, vapour barriers, and minimum code compliance. Your modern timber frame is not failing because wood is a bad building material. It is failing because the system surrounding it was designed for speed and cost, not for the biology of the material it was built from. The medieval barn standing in England since 1292 is not a miracle. It is the result of a system that worked with the nature of wood instead of against it. We knew how to do this. We chose to stop. Subscribe. Every week we dig up the engineering, the material science, and the forgotten building knowledge that kept structures standing for centuries before anyone decided that fast and cheap was good enough. The oak is still growing. The question is whether we still know what to do with it.